I'm excited to share some of the knowledge that we've been generating in this journey that we've been undertaking for the last 2 years to develop technology to address the problem of residual airborne pathogens, and we're targeting specifically large installations like this one. So I've given a fair number of technical talks in my career, but I've never addressed a group of people who are knowledgeable in things like biology, which always scared me to death. But my background is, as Katie said, is in both mechanical engineering and physics. And within those two disciplines, in physics, I've worked mostly in radiation transport and spectroscopy, and in mechanical engineering, the areas of fluid transportation and heat transfer. And I've been very lucky because though the overlap of those two disciplines allows you to work in some very interesting problems. I started out my career working for Union Carbide in solar energy. I've worked for NASA on scramjet technology and various sundry agencies of the U.S. Defense Department on things we probably don't want to talk about. And then recently I got interested in biology and I started biophotonics to try and explore that. And it was in that context that I was working with two of my colleagues, two of the founders of PRS, Julian Martin and Ian Sinclair. And at the time, we were engaged in trying to come up with technology to build efficient and sustainable ways to grow healthy crops indoors to feed the population. And I think it was Julia that said, you know, with all this technology, can't we come up with something to deal with COVID? And can't we deal with the fact that that's airborne? And how can we do that? So to me, it was a great opportunity because I have all these things I've been working on for my career in my wheelhouse, and it was the new problem which I thought was important. And so this talk is probably going to be a little bit different than what you're used to, but I'm going to go through how I approach problems from the ground up. And I may put out information which you go, that's obvious, or you know, why is he wasting our time? But the intent is to show a given problem how you can build knowledge starting with the very simplest ideas. So let's get started. It doesn't get much more simpler than this, and I'm sure everybody here knows this, but prior to 1876, this wasn't known. And so when you talk about infection prevention and control, the first thing you need to talk about is, what does infection mean? And I'm sure it means something to everyone here, but to me it means germs. So when you're talking about how are you going to protect and control infection, you've got to focus in the germs. How do the germs get transmitted from the infected to the uninfected? So let's go through real quick. I'll just do a summary. This is how I look at problems. What are all the ways you could use to control germ propagation? Obviously, mechanical is a good one, filtration, masks. Other types of mechanical also involves things like temperature excursions, autoclaves, things like that, which kill them. Also pressure excursions. You could use ultrasonics or high pressures to kill germs. Second, chemical, the other obvious one, you introduce strong oxidants, alcohols, those types of things into your transmission path. You can have a very effective way of dealing with germs. Third level, we're going to have 5 basic levels here. I'll do them pretty quickly. So what about electrical? How could you use electrical technology to kill germs? Well, the most obvious is through electrical discharges. You know, nothing's going to survive a discharge. Very difficult to implement. But in the area of electrical, there are also technologies like microwave, high-power microwaves, or high-power radio frequencies can be used to kill germs. The fourth technique is optical. And again, we're looking at optical spans a long range of wavelengths from the ultraviolet out to the far infrared. But in order to actually kill, or I should say inactivate, I'll forget to say inactivate, so I'll just use kill for the most of the time. But in order to kill pathogens, you need photons that are strong enough to break or modify chemical bonds. And that really means from the ultraviolet down. So ultraviolet, X-rays, gamma rays. And the last option is nuclear. Obviously, you could use a strong nuclear flux to destroy pathogens since nuclear radiation is very strong. We're talking here about irradiating with neutrons, and I'm sure everybody's familiar with homogenized milk that comes in the plastic cartons that'll last for a year. That stuff has all been exposed to neutrons. So those are the 5 techniques you might choose to eradicate pathogens. What are the 3 transmission modes or paths which they go through, and how do each one of these work on it. And again, I'll go through this pretty quickly. We're looking at the three states of matter here: solid, liquid, and gas. And in our case, we're talking about surfaces for solids. Those are hand transmitted. Liquid is mostly the drinking water, and the gas phase is air. So mechanical is very difficult to do on a surface, but you could probably do it in water and air pretty easily. Chemicals, obviously, if you see the plethora of sanitary wipes and germicidal agents here, again, very easy to do on surface and water. You can think about doing it in air if you introduce things like ozone or ion or singlet oxygen or even atomic oxygen into an airstream. The limitation is basically on how well you can transport those chemicals to the virons, and you're limited here by molecular diffusion. So I just put OK for air because it's very difficult to make it work. Same thing for the next one. It's very hard to imagine electrical systems working on anything but air. But you get down to the optical line, bang, you get 3 green checks. You can use UVC or stronger photons on surfaces for water and for air. Again, nuclear is kind of problematic. You could probably use it on liquids, but you're not going to use it on air or surfaces. So we focused on using UVC to build our pathogen reduction systems to take care of residual airborne pathogens. So let's just talk for a minute about what is UVC. So ultraviolet region of the spectrum is defined as the area just short of your visible cutoff, which is about 400 nanometers, all the way down to the soft X-ray region. But for all intents and purposes, it cuts off at about 200 nanometers, where the atmosphere becomes opaque. So you can't really propagate radiation shorter than that. And the truth is, radiation that is basically longer than about 300 nanometers isn't strong enough to do anything. So the UVC range is around 200 to 280 nanometers. And what's interesting about this range is that it's cut off on the lower end by the oxygen absorption, but it's cut off by the upper end by the ozone absorption. And that's basically what keeps us on the planet, is the ozone layer, which prevents this radiation from coming down and disrupting us. So as a technology for taking care of pathogens, it's almost ideal. You exist in a situation where you can propagate it easily through the medium, and there's no background. And the reason there's no background, as I said, is because of the ozone, and it actually goes into making the UVC particularly toxic to living things, because we've been living under an umbrella of ozone, so our cells are not customized to it. What about UVC? When I started looking into it, I was amazed at how mature UVC technology is. There's a lot of interesting articles out in the literature, but I always use this book, and I'm not plugging it, but it was a guy named Kowalski. This book came out in 2006, and it basically is an encyclopedia of UV germicidal infection. There's data in here on over 200 species of viruses, fungi, and bacteria, the data you need to figure out how to do it. And in fact, in 2017, Kowalski distilled some of it into this publication, which is pretty focused for the interests of most of the people here. So the point is, UVC technology has been around for a long time. It's, you know, the first demonstration of UVC to kill bacteria was in 1877. It's been used to purify water since 1906, okay? So measurements of how it works in the literature are plentiful. It's an easy thing to implement. So I want to just talk for a minute about comparisons of UVC versus chemical versus mechanical techniques. And I should mention, didn't mean to use the word versus in a conflictory context, because we believe that all of these technologies need to be used in concert. Nothing's going to replace any others. We're not going to replace HEPA filters. We're not going to replace other chemicals. But it's worth thinking about some of the differences. Mechanical means, such as filters and masks, don't actually inactivate pathogens. They just capture them physically. And so they remove them from the air or what you're looking at, but you may have a problem in terms of disposal, because if the pathogens have a long life, like some spores do, you could be talking of serious disposal problems for used HEPA filters. Again, chemical means are pretty effective, but in air, those are limited by diffusion. UVC can be pretty well applied across the board, but UVC, and chemical means can all have collateral damage to both humans and materials. So it requires using some care in selecting your mitigation. So HEPA technology is fantastic. HEPA filters work really well. They're easy to install and maintain. They do require, as I mentioned, periodic maintenance and replacements, and those filters used may be biohazards. It also requires electrical energy to push the air through the filter. And the higher level HEPA filter you use, the more power you're going to spend running the air through it. Ventilation also works great, right? If you're trying to get rid of pathogen in a room, you open the window, you clear the room out, there's no question that's a great way to do it. If you're sure there's no pathogens coming in the window. And that's actually happened a few times, anecdotally, where people have ventilated their offices or whatever into alleyways, and other people have gotten ill by ingesting ventilated pathogens. It also is kind of limited by, again, economics, because it costs money to heat or cool air. It costs money to humidify or dehumidify air. And if you're talking about exchanging 100% of the air, which some of the procedures call for that, a lot of HVAC systems have never been built for that. They can't do more than about 30%. If you push them to do 100%, you're stressing the equipment, you may end up with problems. So our system, our PRS system, is designed from the outset to inactivate what we call residual airborne pathogens. And we separated the airborne transmission mechanism immediately into what we called prompt airborne pathogens and residuals. So what is a residual airborne pathogen? Well, as several speakers have talked, virions are containing aerosol particles that are emitted in the breath when you cough or even when you just breathe. And there's a range of sizes from, say, 100 microns even down to 1/10 of a micron. And the larger aerosols, 10 microns down to a few microns, will fall to the ground very quickly. The terminal velocity, if you calculate it, of a 10 micron aerosol is about 1 meter a second. So that's where this 2-meter rule comes. It comes out, it's going to drop to the ground pretty quickly. The terminal velocity for a 0.1 micron particle is 1 micron per second. That's pretty slow. So those are not going anywhere. They're going to stay airborne, and they're going to travel with the air wherever it goes for long periods. And if we don't know for sure how long these viruses or whatever are effective or living, it presents a potential problem. So we call these, the latter types of particles, residual airborne particles, and our PRS is designed specifically to go after what we call RAP. So I'm going to do a little bit of our science here. It's only 2 equations. They're very simple. I'll go through them pretty quickly. Understanding how UV light works can be complicated, and we use very sophisticated optical codes, but you can boil it down into this simple equation, which is the number of 9s that you want or that your system produces is equal to the pathogen kill factor. This is a number that's in the literature. It's measured for several hundred pathogens. You can get it for anything from anthrax to COVID to MRSA. Times the dosage of UVC that you've delivered, how many joules per square meter, divided by 2.3. So if you want 3 9s and you know the K value of the pathogen you're after, all you have to do is deliver that many joules per square meter of UVC. So how do you get D? How do you get the dosage? Again, that's a very simple equation. That's the product of the UVC energy flux density, how many watts per square meter you have, times the exposure time. So this is a very simple way of designing or verifying the performance of UVC-based systems. So what about K? Where does K come from? Let's look at a few cases here. And I've just picked out randomly a few pathogens, starting in the upper left with one form of flu, SARS-CoV-2, goes all the way down to the lower right, which is HIV and anthrax. And the lower the number is, the harder it is to kill. So if you go up to the upper left-hand side, you can see that, for example, measles is almost exactly twice as hard to kill as SARS-CoV-2, right? K value factors are off by a factor of 2. If, for example, you wanted to build a system to kill anthrax, you've got to build something with probably 100 or 1,000 times the flux you would need to kill those other pathogens. So the point is, lots of variations in the value of K, Somebody comes to you with a particular virus, they want to do norovirus, they have the setting. It's relatively straightforward to come up with a design to do that. So this is a little graphic which just is an animation of one of our ray trace programs. And the intent here was to show how our systems use optical cavity effects to illuminate any pathogens from all sides as they go through. And again, the scale on the right-hand side is in watts per square meter. So you can see the green is about 500 watts per square meter. This is kind of in contrast to systems like they use in laboratories where you just illuminate a bunch of pathogens from one side. We're actually illuminating them for all sides. We're getting a much more effective use of the light in there. So what are our design parameters? The first and most important thing for us is safety, efficiency, and sustainability. We don't want to have a big carbon imprint for whatever we do. We want it to be safe, and we want it to be efficient. So our design standard that we use for all of our products is 4 nines of measles, 99.99% kill rate for measles going through our system on a single pass. So if you recall the ratio of the K factors in that equation, 4 nines for measles means 8 nines for COVID. I won't even read off 8 nines because it's too many. But the bottom line is we use a very conservative design standard because we wanted to do this not just for the existing pandemic. That's probably going to be going away in a few years. I think COVID is basically a wake-up call to all of us to let us know that we better start paying attention to what's in the air that we breathe. So another design parameters, we wanted high uniform UV. We want UVC coming from all directions, hitting the pathogens. We also insist on very low UVC leakage levels. The levels in our cavity of radiation are pretty high. We also want a minimum pressure drop in the airflow. The radiation levels in our cavities are very high, and they're on the order of 500 watts per square meter, as you saw that. And just for comparison, if you go out on a sunny day and you lie up in front of the sun's flux, energy flux is about twice that. It's roughly 1,000 watts per square meter, but it's spread all the way from the ultraviolet to the far infrared, thousands of nanometers. Our 500 watts per square meter is concentrated in a spectral band about 1 nanometer wide around the wavelength. So what's called the spectral intensity is many, many orders of magnitude greater than the sun. So again, we've gone through all the testing and certification, both electrical and optical tests to make sure safety is compliant. Our systems all have interlock. If you open them up, they shut down, and so on. The other design mandate is to come up with material configurations that can withstand that flux over the life of the unit. Finally, we had a lot of experiences where we'd explain our science to people who were in the tech area, and they would go, oh, of course it's going to work. If you put that much through, you'll kill anything. And then you go to talk to a business person or a decision maker, and they'll go, nice equations, and we know you're smart, but we'd like to see a demonstration with real live viruses. And so we undertook that, and it took us a long time to find a level 3 biosafety lab that could test HVAC equipment. But we were able to find one in Southern California, Innovative Bioanalysis. They've been around for quite a while. Their staff is very reputable, famous people, and they've been working on way before COVID on these types of problems. So we built a model of our system, and it's shown here. I don't have a pointer, but on the far left is a variable speed fan motor. There's a little transition section, and then the spot with the green dot, glowing green dot, is where our optical cavity is, and the outlet is on the right. So we designed this unit to simulate what's happening in a real HVAC system. And the problem is, in a nutshell, it's very easy to kill pathogens with UVC if you have a long time to do it. If you turn on a lamp in a room or an upper unit, you've got 24/7 or at least 60 seconds a minute for 60 minutes. You don't have to have a very strong light. If you want to kill a virus that's traveling through a 1 meter long section at 6 meters a second, you need flux densities on that level because you only have 1/6 of a second to hit it with enough photons to kill. And on average, it takes about 1,000 photons to kill a COVID. That results in a required dose of 85 joules per square meter. Again, that's what we designed to. So what did we do for the testing? We tested 3 live viruses. We tested SARS, COVID, we tested H1N1, and we tested measles. So again, there's the 3 viruses that we tested, ran live tested, and you can see the ratio of the K factors are about 2 to 1. So the way they run these tests is they nebulize the viruses. They run 3 tests with the lights turned off, collect the viruses, put them aside. Then they run 3 more tests with the same nebulized virus loads. They collect those. They take them out to an external lab, and they grow them for a couple of weeks, and then they have a counting way. And they say, this is how many survived without the light, and this is how many survived without the light. That's where your kill ratio comes from. So they're very straightforward tests. They're very expensive tests. But here's the results that we got for the 3 pathogens that we tested. So the middle column there is the reported kill ratio from the test people. And if you notice, in front of each one of those, there's a greater than caret. And so their results were with SARS-CoV-2, they knew that we got greater than 99.997. We call that 4.5 nines. For H1N1, we got a solid 5 nines. They said, you're doing better than that. And for measles, we got about 4 nines, which is what we were designing the system to, so we weren't too surprised. But if you go back and read the fine print in the report, they didn't detect a single live virus in the first 3 tests. And so what they had to report is the lowest level of experimental resolution. So they could only say, we know you're doing that good or better. They couldn't tell us exactly how good we were doing. So we ran another test in the lab where we turned off 75% of the lights. We only had a quarter of the flux. And the measles measured kill rate was 82.66%. That's almost 1.9. We call it almost a 9. And this is actually a real data point because they were counting viruses after the thing, and they knew before and after real numbers, not that they were off the bottom of the chart. And if you look at the bottom line, these are our optical modeling predictions. We predicted 87.6%. Again, that's almost a 9. The measles, as I said, was 4 nines, but look at the predictions above us that we did. So we're looking at easily, if you have 4 nines on measles, you're going to have 8 nines on COVID and so on. So we believe our systems are very, very strong and very, very powerful. So I want to shift gears a little bit because we took on the problem of how do you build a box that'll kill viruses in central air conditioned systems. And the next question is, how do you deploy that technology in a very efficient way in various situations? And this is an area that some people are just starting to look at, but it's a very important aspect to it. And I think you're going to see more. There's actually people at Leeds University in this country trying to use very sophisticated fluid mechanic models to predict how air moves and how air interacts with radiation fields. But I'm going to just do a very simple model. And again, this is just a model. If you go into a NASA wind tunnel, you see there's a beautiful 747 or something on the ground, and you go, you know, what's that? And they go, oh, that's a model of a 747. You go, what use is it? You know, you can't fly in it, you can't turn the motors on. They go, well, you use a model just to figure out how things are going. We can put that in a wind tunnel, we can measure lift and drag and so on. So this is a model, and it's just 5 very simple mathematical statements. And the first part of the model says, if you intake 1,000 virions, you'll get infected. Now, doctors have come and said, oh, well, you don't know. Somebody with a robust immune system is going to take 33,000, and somebody with a weak immune system, it might only take a couple of hundred. These models are trivial to run. I'm just saying this. I know this number is about in the range that what it takes to have an infection. The second statement is an asymptomatic infected person exudes about 100 virions of breath. Okay? A symptomatic person puts out on the order of 100 million virions in a single cough or sneeze. That's pretty amazing when you think about it. Humans breathe on the average about 16 breaths per minute, and each single breath is about a half a liter. So you can see from this, you've got all the information to do the calculation. If you want to say, well, how long would it take a person to get 1,000 virions in their lung if they have this person doing this and they were breathing at that? And I've run those little calculations for a couple of very simple conditions. One is a single room, okay? So think about 2 humans in a room of about 50 cubic meters. That's like your typical office size. One human is infected but asymptomatic. How long does it take the other person to accumulate 1,000 virions? You assume that the room is well mixed, so the virions go in. That's a fluid mechanic assumption. And the answer is about an hour and a half. So if you're in an office building or business where people are coming up to you and you're interacting with them in a couple of minutes like a bank teller, probably safe, right? You're not going to be around long enough. If you're in a business where people are sitting down in front of you for an hour or 2 hours, you're not safe. So what happens if you put a PRS unit in there that's running at 4 nines, turning over 6 times an hour? And by the way, 6 times an hour is kind of a standard for ventilation. The time goes up to 4 hours. So if you're in the scenario where you're in front of somebody for an hour on average, you're probably going to be okay. If you look over and you see a roommate at the next desk over and you're sitting next to that guy for 8 hours, you might not be okay. So if you take this same PRS, you keep the same amount of photons floating around, and we just turn up the speed so that instead of getting 4 nines, we only get 1 9, but we can turn the room over a lot quicker, say 24 turnovers an hour. The time goes to 14 hours. So you're probably safe on a full day with a guy next to you. And so, you know, I've talked about a single room here, but what happens if we do this for a multi-room situation? So I'm taking, and I said hospital, but this probably applies to a lot of multi-room things. So now we consider 10 rooms, each one with about the same volume. One room contains a symptomatic person who's sneezing and coughing about 1 time a minute. And in the calculation, we're going to throw away 90% of the aerosols that come out of his mouth. We're going to say they're heavy, they're going to drop down. We're going to take that flux at 10% of the actual value. The question again is, how long would it take a person in another room to accumulate 1,000 virions? You assume that all the rooms are serviced by a common HVAC system. It has a PRS, and again, the turnover time is about 6 times an hour. So the answer, less than an hour with no PRS. So if you're in a hospital that has, say, adjacent wards served by the same HVAC unit, and somebody in some ward ends up with norovirus, the other ward's going to be infected in a very short time, an hour at least, certainly within a day. If the PRS unit is a 4 nines unit, it takes 7 hours. So in a hospital, that's pretty good. If you're going in there for an x-ray or something, you're going to be okay. If you're in there overnight for surgery, and you're going to be there for 20 or 48 hours, you're probably in trouble. If you now crank it up to 7.5 nines, which is what our system demonstrated, the time for that person to infect 1,000 virions goes up to 23,000 hours. That's 3 years, okay? So this difference between central systems and, say, room systems, in a central system, you got to get every last one. You can't allow them to spread. I talked about a hospital, but imagine for a second that this is your office where you work, and the guys across the hall in a different company aren't as good as your guys at keeping them, and somebody comes over there and starts coughing into the common system. Those statistics will apply to you, and then take it one step further, and imagine if you live in an apartment building or a condominium, okay? You're there 24/7 with your family and your loved ones. You really need to have that high protection for a centralized system. So I think that pretty much demonstrates the need for building these studies where we're trying to figure out how do you deploy these different UVC systems, room units, upper air units, whatever, in a logical way to accomplish whatever goal we're trying to do. Now, I was going to do a little anecdote, but I don't think I have the time, so I'll just slip into the closing here. We used to live on a planet where we could go out, we could go to the store, we could buy food off the shelf, we could drink tap water. We didn't have to worry about anything, and that was maybe 20 or 30 years ago. Now we're in a situation where a lot of us, I do for sure, drink only either bottled water or we put a carbon filter. So a lot of us will filter our water. We happily pay 20% or 25% premium for get food that says organic, because we believe that's better for us. But there's nothing in there about the air we breathe. And I really believe that in the next 10 years, because of the wake-up call for COVID, that we're going to be moving to an environment where everything is made safe to consume, the food, the water, and your air. And I know we've been talking to large landholders in London, and the millennials are projected to take over something like 70% of the office space in the next 7 years. And some of the things have shown that millennials interested in money like the rest of it, but they will not come back to work in a place that they don't think is safe, okay? We used to live in this incredible spaceship called Earth, and we kind of mucked it up a little bit, and we're moving towards where we're going to be living in individual spaceships in the future. And I think that systems like PRS are going to find, you know, a very important application there. So again, last conclusion is the application of UVC is proven, but to make it work, you've got to do care and modeling in the air. Collaboration is essential, you know. If you talk about optimizing energy, you're probably going to end up with a situation in which you can back down the HEPA requirements by a couple levels and put in a PRS and end up with lower energy. So we're all looking beyond COVID. We believe that airborne pathogen mitigation is important. And I would invite, you know, come to our booth if you want to hear more about this technology, about how it might be useful for you. Or if you're in the UVC business, I can walk you through those estimates to say what the kill factor for your application is. We're happy to share anecdotes. We've had pilot systems running for 18 months, various number of settings, and we can share those at Pathogen. That's it. Thank you.